Okay, so it is my great honor to introduce somebody who needs no introduction, Steve Yablo from MIT. Of all the influential things that he has written, I think the most relevant, haha, is his book Aboutness, which set an agenda for many of us, and I think just has been so influential and inspiring. So please join me in welcoming Steve Yablo.
Hi, everybody. I'm sure that was rapturous applause. I couldn't hear it, so I just supplied that. But there's the Zoom toggle I can do that just sticks in applause where I feel it's appropriate. So I have fallen in love with this conference from a distance. That might say more about me than about the conference, that it's from a distance. But the talks have been inspiring. I just cannot believe the amount of good work that's being done in these areas. I'm going to spend the next few days just like poring over your slides. Thank you so much. Thank you, Erica, Martine, Justin, Lucas, basic organizer, and everybody. So I'll start. One thing I've noticed is that there's been very little history in this conference, and so I'm going to repair that by having a half of a slide where I mention two historical figures by name, Bayes and Brentano. Here we go. So the principals are now going to meet. That's Bayes, Presbyterian minister, mathematician. We know him for the rule that he suggested about how to adjust our level of confidence in a hypothesis when evidence E is acquired. So, of course, he didn't really do that. I mean, it's really hard to figure out what he did do, something to do with binomial distributions. H had beforehand a probability conditional on E. That's conditional probability, explained in a minute. That conditional probability then gets promoted to be your unconditional sort of monadic credence in H after you learn that E. So in other words, you're already prepared in a way to receive the information that E, and you knew what you would do, so to speak. That's encoded in your conditional probabilities, and so you just go ahead and do it. So your new credence in H is your old conditional credence in H on E, where that is explained traditionally as the ratio of the your old credence in the conjunction of H and E, that divided by your credence in E. So that's Bayes. And you probably remember this guy, Brentano. His idea was that mental states are directed. They have an intentional object or subject matter. Exceptions have been noted or alleged: undirected anxiety, nameless dread, but at least for propositional attitudes, fying that E, the idea is pretty plausible. So I'll let his thesis be about fying that E involves intending to small bold E its subject matter. So far, these look like unrelated ideas, but there's a connection, because let phi be the attitude of belief. If, as Brentano suggests, believers attend to the subject matter of the sentence giving the content of their belief, attend to small bold E, so also presumably do those with a certain degree of belief. It's not as though anything fantastic changes when you go from being 100% certain that E to being 99.5% sure that E. So there is probably or plausibly something attached to having a credence in E that's similar to what goes with belief, namely some kind of attention to its subject matter. Bayes' rule for update, classical update rule, beacon, is strangely uncurious about the subject matter bit. It asks only for the sentence's intension, bold E, the set of E worlds. The probability of E would standardly be the measure of that set. If you have a probabilistic measure on the space of outcomes. So E's aboutness properties are completely ignored. Now, I say that Bayesian update is strangely uncurious. Things aren't always appearing in the order I had in mind, but let's do it. But curiosity would be strange if subject matter was evidentially irrelevant. So let's ask about that. Let's check. Subject matter, for our purposes, is made up of the sentence's exact truth makers, epsilon. Probability of E is a function of their probabilities, singly and together. So I'm counting both truth makers and conjunctions of truth makers. Of course, sometimes those are counted truth makers, but I'm assuming not. And I'll call those things T makers. So T makers are also written epsilon variant font. Probabilities of these T makers, epsilon, determine the probability of E. So to give the simplest example, say E is at its junction, A or B. E's probability is the probability that one of those, that it's true somehow or other, in other words, that one of those two truth makers holds, which is, as we know, just from facts about intersection and overlap, the probability of A plus the probability of alpha plus the probability of beta. And now you have to subtract back the probability of their intersection because it was double counted when you added the probability of alpha to the probability of beta. So there you have E's probability as a function of the probabilities of its T makers. I like to think this is like an image that plays a big role in my thinking. Think of these T makers as like a school of helper fish. Like, so E is there in the probabilistic waters, and we're going to update on E when it breaks surface. So surface is probability 1. And alpha, beta, and their conjunction or their fusion are like a school of like helper fish that are nudging E up. Like E is this big lumbering, not very nimble fish, and it's sort of jostled around in the water by alpha, beta, and alpha, beta. And in this case, E is nudged up to 1. But there's any number of things that the helper fish could have been doing to arrange this, as many as there are reals in 0, 1, such that R plus S minus T equals 1, where R is the probability of A, S probability of B, and T is the probability of the conjunction. So here in the picture, you've got the big fish is probability is E, and it's at probability 1, you see on the right. Beta is like pushing it up from the front end. It's a probability 2/3. Alpha is pushing it up from the back end. It's a probability 1/3. I'm assuming here that alpha and beta are incompatible. So the probability of alpha, beta, that's a third fish. There actually is a thing in biology. Well, of course, there are beta fish. But there's also a thing, an alpha beta fish, which is like an alpha member of a clan of beta fish. Look it up. Okay. So here we've got this somewhat complicated structure. What the kind of Bayesian sees is E breaking the surface when it hits probability 1. But the Bayesian's kind of not paying attention to the probabilistic churn below, which can take a lot of different forms. So are truth maker probabilities just supposed to be ignored? It seems like that would be very strange. That would be like ignoring what a thing is made of. Say, is it made of gold or is it made of coal, and deciding its value? Just look at the whole thing. Here it is. I've made it. Those materials are in there. I don't want you to look at them anymore. Just tell me how much you want to pay for it. Well, in the same way that, say, a hunk of matter is made of materials, E's truth consists in the holding of certain epsilons. Those shouldering more of the burden, probabilistically speaking, ought to get more of a say. So if beta favors H, then since this is probability 2/3, alpha would have to strongly disfavor H for H not to be supported on balance by alpha or beta. I'll say in the underneath in the footnote, so the T makers, the truth makers closed under disjunction. Let me just add the DT makers are the T makers closed under disjunction. So there's something, they're related to what Kit would call disjunctive and Mark would call disjunctive parts. Okay, rigidity. Truth maker, neglect is not an accident. It's written into the rules DNA because BCOD is often just defined as the one and only way of adjusting your credences that first brings the newly acquired evidence up to 1, but is second rigid in the sense that probabilities conditional on E don't change. So the new probability of X on E, which just is the new probability of X because E is probability 1, is the old probability of X on E. So from this, it actually follows very easily that any F that's stronger than E, any strengthening of E, the whole bunch of them have got to appreciate at the same rate, and indeed that rate is fixed. They appreciate it at the same rate that E does. They're all multiplied by the reciprocal of the old probability of E. So we've got F entails E's. So the new probability of F is the old probability of F given E, which is the old probability of E and F over the old probability of E, which is the old probability. Since E and F is equivalent to E, F being stronger, that's the old probability of E times 1 over the old probability of E. So they all appreciate at that rate, 1 over old probability of E. And of course, truth makers are E impliers par excellence, so they appreciate at that rate as well. So no wonder, at least we can start to see why BCOD doesn't feel the need to ask about probabilistic underpinnings, probability of these epsilons. There was only ever one option. The new probability of epsilon is the old one divided by the old probability of the newly acquired evidence. So underpinnings are in effect stipulated. But what do you mean they're stipulated? You can't stipulate everything. Who gave the classical updater that power? It's not the theorist who decides these things. It's the worlds. It's the world. T makers, epsilon, are going to have all kinds of probabilities. It depends, as we're about to see, on how the sentence is learned. There are many ways of learning a sentence, and they involve different sort of configurations on the part of the probabilities of the T makers, which we just saw have as a resultant the probability of E. So I call this underpinnings. So here's like the generic scenario. Betty, and Cleo toss coins. Your money is on all 3 throwing heads. You're happy to hear that A or B, Al or Betty threw heads. The original probability before you heard this of one will throw heads was 3/4 because the probability that they would both throw tails is 1/4, a half times a half. And it now becomes 1. The initial probability for Al and Betty throwing heads was 1/4, half times a half. And probability of all 3 throwing heads was therefore 1/8, half times 1/4. And what do they now become? Well, that depends. Alpha, beta, and alpha, beta can't stay at their old values. They were half, 1/4, or this sum that I said gives you the probability of A or B is going to be stuck at its old value, which was 3/4. So we got to come up with some new underpinnings so that P alpha plus P beta minus P alpha beta is 1. And you can imagine continuing many underpinnings. So I'm just going to have 4 that I'm constantly working with here. So look at the top 2 lines of this. Can you see my cursor? Or no, maybe. So the top two lines. Before, A or B was 3/4 likely, as we said, just because the chance of two tails is only a quarter. Al heads was half likely. Betty heads was half likely. Both heads was a quarter likely. All three heads an eighth likely. What happens after you learn that A or B? Well, certainly A or B goes up to 1. First understory. Underpinnings, call it. First underpinnings. L heads goes to 2/3. Betty heads goes to 2/3. Both heads goes to 1/3. All three heads goes to 1/6. Of course, mathematically, I can just choose numbers smaller between 0 and 1 almost at will for alpha and beta. I mean, they better add to at least 1. And then alpha beta is actually determined by that, because by the equation that I just mentioned. So I'm just like giving a few almost at random here. The second underpinnings is 3/4, 3/4, a half, and ABC is a third. The UP2 is 7/8, 7/8, 3/4, and then 3/8. UP3, 9/10, 9/10, 4/5, 2/5. Those are 4 different underpinnings you could have for the probability of A or B being 1. And the probability of ABC, as you can see, is up in the air until we decide which of these probability assignments to the T makers we're going to go with. Well, how do we decide which we're going to go with? Well, those values derive in turn from the probabilities of this or that T maker sending the sentence your way. Like, who is sponsoring this message? You get this message. E drops into your inbox, and you have to say, well, yeah, okay, but it carries certain baggage with it, right? It's these T makers are going to have experienced certain changes to get E in there, and you got to have to speculate about what happened, because it can make a huge difference. So accounts of which epsilons probably sponsored the message are backstories, and I'm going to give you some backstories. So here's a picture. Lefty and righty, 2 coins, one on the left, one on the right. They're flipped side by side. One is Al's silver dollar. The other is Betty's loonie. Loonies are Canadian metal dollars. Something is seen that makes clear that A or B, but not whether A or whether B. What was seen? So 3 scenarios. In the first and Bay's friendliest, you don't really see any coin land. The curtains draw shut right away. And then somebody puts out a sign saying, not both landed tails. It could have been a machine that decided that had a way of registering that not both landed tails. The second has lefty in view, still in view. And you see lefty land heads. Righty is still hidden. Blast has 2 sightings of lefty 1 and then lefty 2. They may or may not be the same coin. Both are heads up. And these actually predict the underpinnings that I gave you. So here's the first one. I call it unseen. This is the one Bayesians like. This is the only one that Bayesian update gives the right answer for. Lefty and righty line behind their respective curtains. A or B is conveyed by testimony. We read the sign. This supports the first underpinnings, UP0, 2/3, 2/3, 1/3 Y. Well, once you hear that one of the coins came up heads, there's really 3 possibilities. Both heads, just Al, just Betty. They're equally likely. They sum to 1, so each is a third. Probability that Al's coin came up heads is probability that came up heads with Betty's or without Betty's. So you add those, 1/3 plus 1/3 is 2/3. Similarly, for the probability that Betty landed heads, all this is as Beacon predicted. So if you just do the math, the old probability of A or B was 3/4. So the new probability of L throwing heads is the old probability, which was a half, divided by the old probability of one of them throwing heads, which was 3/4, and that's 2/3, which is just what we got. Now, one scene. This is the one I'm going to be coming back to again and again. This is the important one. And there's a certain history to this. This is sometimes known as the two children puzzle. So A or B, you're told. So you know that a coin landed heads. A and B, if and only if the other coin landed heads too. So the probability of the other coin landing heads would seem to be a half, right? So probability that they both landed heads is a half, not a thirds. So this was the subject of article in Scientific American, well, at least one column in Scientific American by Martin Gardner, Mathematical Games. And he initially thought this confused, and we'll see various ways that it could be confused. But it needn't be. He eventually decided A or B could have been learned like this. We could have seen lefty land heads. Lefty is as likely Al's dollar as Betty's loonie. Righty, we don't know. The curtain was pulled before Betty's coin landed. So I'll call lefty heads lambda, righty heads is rho. Probability that lambda and rho is probability of lambda times probability of rho. That's 1 times a half, because we know lefty landed heads, and we don't know anything about righty. But of course, if lefty and righty both landed heads, then so did Al's and Betty's coins, because that's what they are. So we can say that the probability that Al and Betty threw heads is a half. Now, the probability that Al threw heads, this is what's interesting, is the probability that you just saw Al throw heads, which we just said is, which is a half, because it could have been either coin, plus the probability that you actually saw Betty's coin land heads, but Al's coin landed heads off camera, so to speak, off to the right. So that's a half plus a half times a half, 3/4, and same for Betty's coin landing heads. So the backstory, BK1 generates the underpinnings BK1. Okay, 2 scene. I'll just do this one really quickly because it's not going to be, I just want to give you a sense of the possibilities. 2 sightings are made on the left, both of heads, one after the other. So the coin is, you see a coin land, and then the coin is, and then a coin is brought out again in the position in which it landed, but you can't tell whether it was the same coin as the first time. So the probability that you see both alpha and beta is the probability of what I called 3, alpha and beta in either order. Probability that you saw alpha is probability that it wasn't beta twice. Probability that you saw beta is that it was an alpha twice. And these fix the probabilities of the events we care about, whether else and Betty's coins landed heads. So I'm going to write script S square brackets theta for seeing theta. Probability of alpha is the probability that you saw alpha plus probability that you didn't, that alpha happened unseen. Likewise, and if you figure that out, times the probability that you didn't see alpha. If you figure that out, that's the probability that you saw alpha plus 1 over 2. Similar thing for probability of beta. Probability of alpha beta, you can figure out from that, is the sum of the probabilities of seeing alpha and seeing beta divided by 2. And this yields the second understory. If the probability that you saw alpha is the probability that you saw beta is 3/4. And you can imagine someone just telling you this. The probability that you saw both of them is a half, and it yields you P3, the third underpinnings, if the numbers are instead 4/5 and 3/5. And almost any underpinnings can be obtained by such means. Okay, am I going too slow? I hope I'm going to speed up a bit. All right, Bayes at bat. So there's these, you see there's these like 4 different backstories, and you see them on the left, and there's 4 different underpinnings you see on the right. And the only one that Bayesian update gives the right result about, as far as figuring out, let's say, what alpha beta is, probability of alpha beta, is the one subscripted 0. So Bayes says the chance of 2 heads is a third. But if any of the other 3 backstories held, it's really a half or 3/4 or 4/5. So, and of course, just the fact that the information that A or B has come in doesn't tell you which of those backstories was involved, and therefore which of these underpinnings holds. So Bayes' rule, to go by this chart, is betting 250, and adding further scenarios would push the average lower, as low as you like. How is this not a reductio of Bayes update, Bayesian update? Well, here's the reply I expect. Look, rules are tools. You don't want to use them incorrectly. They come with a manual telling you what the correct use is. And the manual for Bayes' rule says for inert E's only. So inert E's are E's, each of whose truth makers sort of appreciates probabilistically at the same rate as E. So like I say inert, I'm thinking like chemically inert. So you think of the constellation, E and its truth makers, and they kind of, their relation is frozen. They all kind of multiply at the same rate. Okay. So you can think of this as kind of a top-down situation. In a way, E rises, the impetus, the dynamic impetus is E rising to 1, and then the epsilons are dragged along behind. That's what an inert E is. Otherwise, I call E active. So Bcon is intended for inerties. And Bcon, on the cases for which it's intended, is batting 1,000. So that's a response. 3 replies. This is just trivial. Inert just means Bcon satisfying. It just means things are, the epsilons really did deserve the credences that Bayesian update gives them. It's like saying I bat 1,000 on my hits. I don't hit very well, but on my hits, I'm perfect. It's also circular because, or at least it creates circularity problems, because one needs the probability of the T maker's epsilon to test for inertness. That's how you got to figure out that you've got to test each of these to see if it's the old probability of epsilon divided by the old probability of E. But to find new probabilities, you have to use Bcon. But you're not supposed to use it unless you've tested for inertness. But you have to use Bcon to find these things that you need to test for inertness that are the sort of entry condition for Bcon. So that's the circularity. And it's also it's stultifying or self-defeating. Inerties are kind of special. They're the kinds of things you learn while not paying any attention to the subject matter of the sentence. Because if you look at the subject matter, you're bound to notice something about how it's likely true. It would be amazing if the truth maker's probabilities stayed completely fixed when you looked at how the world was configured with respect to the subject matter of E. So this is like a joke I heard a lot when I was a kid. Doctor, it hurts when I go like this. The answer, this is a Henny Youngman joke for those of you who like Borscht Belt comedy. So don't go like that. Reverend, your rule leads me sometimes astray, which it does 3 out of 4 times in this diagram. So use it the other times. That's basically, as far as I can tell, that's what Bayesians say. I haven't heard this discussed explicitly very often, but that's what they say. You use it on the right occasions. Okay, so a rule for non-inert active evidence would be nice. 3 obstacles. One is we're used to updating uncertainties. That's how Bayes' rule works. What the probability of a T maker is less than 1. Well, there is a way of dealing with this that Jeffrey came up with a long time ago. Think of the sentence as ambiguous between these 3 ways of being true. Then here's what Jeffrey gives this example, famous example: observation by candlelight. The agent inspects a piece of cloth by candlelight and gets the impression that it is green, although it might be blue or even violet. Originally, his degrees of belief in green, blue, violet were blah, blah, blah. His credences afterwards are 0.7, 0.25, and 0.05. So let's generalize from this. Say X is the disjunction of incompatible alternatives, Xi. H's new probability should, he thinks, be a weighted average of its old ones conditional on the Xi's. So that's Jeffrey's rule, Jeffrey conditionalization. Probability of H is the sum of the probabilities of H conditional on Xi times the probability of those Xi's. So it's like a weighted, you look at how probable H is in each cell of the partition, and you basically take the average, bearing in mind that some of the cells are more probable than others. So this right-hand side here might look familiar. It's what's known as the expectation of the old probability of H conditional on Xi, considered as a random variable. So let me just quickly review how random variables work. A random variable, typewriter font V, is a function from partition cells Zi to real numbers, so the total mass of the stars. So they're related to subject matters. It's like a function from, given a subject matter, it assigns a real number to each cell of the subject matter if it's a partitional subject matter. So the expectation of a random variable is the sum of the products of the probability of the cell with the value of that random variable in that cell. And the constraint here is V has a fixed value in each cell. So Jeffrey's rule just is the case where the ith cell is the old probability of H conditional on Xi. So the Xi's here, the cells, Jeffrey's partition cells, are a bit like truth makers. In fact, in his own example, green or blue or violet, they probably are truth makers. X can hold in various ways, X1ly, X2ly. If we knew which of those really obtained, if we knew how things really went down X-wise, we condition on that. We condition on X check, the one that really happened. We don't know, so we have to guesstimate, and that is, the guesstimating just is taking the expectation of H's probability. This is a random variable. H's probability given however it is that X actually holds. So that solves one problem, but there's a couple more that now occur. One is these truth makers, epsilon, rarely form a partition. So take A or B, as you know, it's truth makers, L heads, Betty heads, both heads, any two of those overlap. The issue with non-partitions is that overlap worlds are going to be double counted, and then the result, if you apply Jeffrey's rule, you won't get a probability function because it won't be normal. Probability of, say, A or B will be over 1. Jeffrey hints at the possibility of generalizing JCon to allow for overlap, and there are definitely things one could try. Another option is to partition on which truth makers obtain. So worlds are equivalent. Here's a subject matter. We call it the truth in E. The truth in E is a subject matter. Worlds are equivalent with respect to that subject matter if E has the very same truth makers in them. then you could say the probability of H is the sum of the probabilities of H conditional on the truth, different hypotheses about the truth in E times the probability that those hypotheses are correct. So E super K ranges here over E-consistent state descriptions, where you take all the truth makers and you toggle them up or down. One of them had better be up or it won't be E-consistent. So let's not pursue this, because T makers are unsuitable for another reason as well, and our response to that other reason will get us back partition. So cell probabilities have to be available pre-update. I mean, they're fed into the rule. They're the weighting factors. So you have to know how probable each cell is. But T maker probabilities, apart from certain special examples which Jeffrey tends to focus on, often aren't. So for instance, in the case of, go back to one scene where we see one coin come up heads, could be L's, could be Betty's. Al heads is 3/4 probable in that case, I suggested. So half a chance that you're seeing Al's coin coming up heads, and a half of a chance that that you're not seeing Al's coin, and a half of a chance in that case that it came up heads. So that's 3/4. So, but you don't see that Al's coin is 3/4 probable. Al's coin heads is 3/4 probable. In fact, the chance is only a half that you're even seeing Al's coin. Rather, the seeing, call it script S, has probability a half of being of alpha, probability a half of being of beta, probability 0 of being both alpha and beta, and we go from there. So, but if the probability that Al's coin came up heads remains to be determined, then the obvious thing to try is to condition on its determinants, which is the probability that you're seeing alpha or seeing beta or what have you. Now, these don't themselves form a partition, because you might be, in principle, seeing several truth makers at once. Not in the case I mentioned, but in others. So let's condition instead on the probability of O, we have these double brackets around theta, that theta is all that's presented. So that the total meaning, if you like, of O is theta. And it's a win-win, because the inter alia probabilities that we were talking about before are recoverable, because the probability that epsilon, a T maker, is presented is the sum of the probabilities of the total meanings whereby epsilon is the case. So the probability that O means alpha inter alia is the sum probabilities of alpha plus some other stuff being what it means in toto. Okay, so now we got a flow chart we can work with. Now we're in business. Question was, what is sentence's evidential import? And we said right at the beginning, look, you got to answer that, you've got to answer this. What are the probabilistic underpinnings of that sentence's rise to 1? And that depends in turn on how E was learned. So what are the probabilities of O meaning epsilon I inter alia? And then that depends on how should probability be distributed over hypotheses, theta double brackets, O double brackets theta K about O's total meaning. And it's this last distribution over total disambiguations that we bring to the update table. So it's roughly, it's kind of like you're looking at a photograph, and it's not clear who's there in the photograph, but there are hints, and you can sort of form surmises. You say, oh, look, that seems to that's got 3/4 of a chance of being, Voltaire, and that's, well, photograph wasn't, it's a painting. 3/4 it could be Voltaire, could be Leibniz, could be Newton, blah blah blah. And you can distribute probability over hypotheses about this. So we're going to amend the rule. Remember, we had before the truth in E. That was a function from E worlds W to the conjunction or fusion of E's obtaining truth makers in a world. That's, so to speak, if you think of like variable composition across worlds, like a statue being made of slightly different hunks of clay, E's truth is made of slightly different truth maker combinations in each world, or in different worlds. So H is expected probability conditional on the truth in E. That's essentially what Jeffrey conditioning would give you. That would be great to know, but it depends on the new probabilities of these truth maker combinations, which remain to be determined. We just saw in the case of you don't see Al's coin probably landing heads. So the truth in O is what we're going to substitute here, and it's very much like the truth in E, but it has presented truth makers in place of truth makers or fused truth makers. And the advantage here is it's relatively available because it concerns what's in view, whereas probability, say that Al threw heads, is the probability that you saw Al throw heads plus probability that you didn't see it, but it happened anyway. Okay, so here's our picture. What credence in H is licensed by an event O of E learning? So we know Bayes' answer. H is probability conditional on E. Jeffrey's answer, H is probability conditional on the truth in E, more or less. Us, H is probability conditional on the truth in O, the truth in the learning event. The way E came to you, I'm thinking of it, I'm going to wax poetic here, comes like trailing clouds of truthmaker glory in the form of probabilities of its arriving from this direction rather than that. So ACON, this is the rule for active learning. Your new credence in H is the sum over thetas, which are thetas are right as I've explained things so far. Thetas are T makers, but I'm going to change that in just a sec. Sum over T makers, the probability that the learning event has put that T maker on display in toto times the probability that that's what has happened. So it's the expectation of H conditional on whatever O is really telling you about the world of truth makers. Problem. Look, O sometimes brings word of no particular T makers. Probability of O telling you that theta is 0. If theta is a T maker, so for that, so ACON as written goes trivial in that case, where it says the conditional probabilities are always, well, either undefined or 0. So the way we address that is we extend theta to truth makers or T makers closed under disjunction, DT makers. So we know that some of them are presented because E's truth condition is the disjunction of all its truth makers. That's certainly presented, or O would not be a vehicle for e-learning. You take yourself to be learning that E is true somehow or other, or you wouldn't think you were learning that E. I'm not worried here about like ignorance of E's truth makers. I'm taking all that to be transparent. So Bayesians see E's truth condition as its total meaning. That's why learning for them is, if you like, pure learning that. A arrives as a lump, and all you find out about it is that it's true somehow or other. Of course, you already had views about the likelihood of its truth makers from before, because you're opinionated about everything, just about. But those are simply fed into the machinery, and they all get multiplied by the same value. Okay. Sometimes the disjunction of the epsilon i's is O's total meaning. So when the sign says that Al or Betty threw heads, it doesn't tell you anything else. The probability that you're seeing, so to speak, through the sign that Al's coin came up heads is 0. Or you could actually make it be non-zero. Indeed, you could arrange it so that instead of a sign, a heads-up coin is shown, which could be Al's coin or could be Betty's. But when you do the math, it actually winds up giving the same result. E is still inert. So Acon agrees in that case. Whoops. So Acon agrees in that case with Bcon. The probability of H conditional on the total meaning of this observation, I call it an observation, it needn't be, is about the probability of H conditional on E. I mean, there might be differences on the margins. Often, though, the probability that O means in toto theta is greater than 0 for stronger thetas, and that's when things get interesting. So here's things getting interesting. So certain kind of implicature, what's called an implicature. So suppose I say, look, or someone tells you Al threw heads or Al and Betty threw heads. Stefan Kramer has a great example of this kind. The doctor tells you, your ankle is sprained or it's sprained and broken. Anybody would consider, anybody would see in this evidence for my ankle is broken. Not conclusive, but it sort of makes it more probable. So it's good news intuitively for B. But of course, A is not good news. Al's throwing heads is not good news. And same proposition is expressed. So usual answer to how A or A and B gets to be better news for B than A. Look, context pragmatically strengthens A or A and B in a certain way. People have studied this in great detail in linguistics to include implicatures. Implicatures are kind of folded into the strengthened meaning. Our answer, no, A or AB always supports B, except in one really weird case where context forces a super weak reading. So what is the new probability of B? It's going to be its expected probability conditional on O's true meaning, or the truth in O. So first imagine that the news you hear, what you hear is A. A has just the one truth maker alpha. There's only one thing that A learning can mean. So the probability, the new style conditional probability of B on A is the probability of B conditional on that you heard that A, or observed that A, or whatever, times the probability that you did observe that alpha. Sorry, I should have said alpha both times. Well, probability that Betty's coin came up heads, given that you saw Al's coin coming up heads, is a half. Probability that you saw Al's coin coming up heads, given that you've learned that A, is 1. So the product is a half. But now switch to learning that A or A and B. That can mean either alpha or alpha and beta. Alpha fused with beta. Say the first with probability K, the second with probability 1 minus K. Now the conditional probability, as figured by the kind that comes out of Acon, is going to be, and if you just figure it out, let me not waste time on the calculation, it's going to be 1 minus k over 2. Because there's a 1 minus k chance that you actually saw both coins coming up heads, in which case the probability that Betty's did is 1. And so, yeah. So you get 1 minus k over 2. And this is bigger than a half, provided that k is less than 1, which is the same as provided that there's a non-zero probability that this message came to you courtesy of both throwing heads. So A and B fails to support B only if sent by an event that definitely does not present alpha and beta. That can happen. You can, as we'll see, you can imagine a case where somebody hears that L through heads and says, for no good reason, like in a Gettier case, just decides out of pure caprice to add on as a new disjunct A and B. That's the case where you're not hearing anything about Betty's coin. But it takes work to arrange. A or AB is, just by its truthmaker meaning, raises for our update rule the question of what the probability should be that you've just seen alpha and beta, or you've just received word of alpha and beta. And B favoring answers hugely outnumber B neutral answers. The one B neutral answer is 0. The B favoring answers are all the other real numbers between 0 and 1. Okay, a paradox. You may have heard of this. You should have if you haven't. Wheel's paradox. My coin, C naught. So infinitely many coins are tossed behind a curtain. My coin landed heads, C naught. That's the hypothesis. One piece of evidence I might receive is all but finitely many of the later coins landed heads. Another is all but finitely many of all the coins landed heads, including my coin. Well, the second seems like better news for my coin landing heads than the first. But people say the arguments pointing that way must be fallacious, since the conditional probabilities are the same, because D and E are hold in the same worlds, because one coin can't make the difference between whether infinitely many did landed heads or finitely many did. So people say you're just going to have to explain this away. The probability of H given D is clearly a half, because D doesn't even address my coin. So the probability of H given E must be a half too. So claim. Well, the new style conditional probability, the one that sort of feeds into learning for conditioning for active learners, is more than a half. So why think that? Well, E's truth makers, which are the same as its T makers and DT makers, are of the form all SJs are heads, where SJ ranges over cofinite subsets of the set of coins. Cofinite meaning that only finitely many coins are excluded. So those are the truth makers. All SIs are heads. Importantly, I don't say exactly the SIs are heads, because that doesn't really add anything. That would be an irrelevant accretion from the point of view of making it true that all these coins landed, that all but finitely many landed heads. It doesn't care whether any landed tails. So the probability of H given E, the new style conditional probability, is the expectation of the probability of H given that we've received word that the SJs landed heads. And that's just really the expectation that C is a member of SJ, which in that case, it's definitely, my coin definitely came up heads if it's a member of the set of the ones that did, plus the expectation that although my coin isn't a member, it still came up heads. So that's written out there. When you figure it out, it's m plus 1 over 2, where m is the expectation that my coin is a member of the set of the relevant cofinite set of coins. So that's at least a half, clearly. It's a half only if m is 0. Talk about m plus 1 over 2. That is, it's more unless, for it to be a half, you need that C is certainly among the finitely many exceptions. C is certainly among the finite. So that's crazy. No way C is certainly among the finitely many exceptions. Probability, the new probability of H is going to be greater than a half. How much greater? Well, let's just suppose, which seems like a very modest assumption, C is at least as likely to be among the cofinite multitudes, in other words, the all but finitely many exceptions multitudes, as the finite few. Then the probability of H given E is going to be greater than or equal to 3/4. Induction. Am I out of time? No one said anything. Maybe if I was looking in the chat. Okay. The straight rule, as I'm conceiving it. Probability that B is F, where B is a thing that hasn't been observed, set aside for later observation, given that the AIs are F, is greater than the probability that B is F. That's what I'm calling the straight rule in a probabilistic context. Does this rule commit us when the predicate is GRU, Rx, green and observed, or not green and not observed, to expecting B to be non-green on learning that the AIs are GRU? Well, I mean, you really ought to scratch your head just at the form of the question here. The straight rule contains nothing about updated probabilities, so it doesn't tell you anything about expectations. Oh, chat. So wait, let me. What is that? Okay. I think I can do it in 6 more minutes. Thanks. Oops. So it doesn't tell you anything about expectations. The straight rule plus Bcon may commit us to raising our credence for B is GRU. But Bcon is for pieces of evidence whose truth makers all get likelier. And the truth makers for, let's suppose there's just one A. The truth makers for A is GRU don't. The probability that it's green and observed rises, while the probability that it's not green and not observed falls to 0 because you just observed it. So it's a job for ACON. And when you figure it out, the straight rule actually winds up telling you that your probability for B being GRU should actually go down when you factor in the fact that you learned that it was GRU, that A was GRU, by learning that it was green and observed. So I won't go into that, into the math. Goodman says straight rule generates gruesome expectations that the new probability that B is not green should exceed the old one. Our contrary suggestion is that it generates no expectations at all, absent an update rule that you're going to feed the finding that A is GRU into. It generates B isn't green expectations when fed as it shouldn't be into Bcon, but it generates the right expectations when plugged as it should be into ACON. Yeah, okay, let me know. Inference. Almost all heads is said to be better evidence than almost all heads C aside for my coin landed heads. But if I know the one, I can infer the other, giving myself, this is objection and further directions, future directions. If I know the one, I can infer the other, giving myself thereby the evidence that I supposedly lacked. Well, go ahead and try. But remember that E's evidential powers vary according to how it made its way into your belief box. You see L's coin land heads. That's OA. You infer ARAB. That's OARAB. If seeing L's coin land heads did not put Betty's coin landing heads before you, probability that you were seeing Betty's coin land heads is 0, then OARAB doesn't either, because it gets its meaning from OA. It's not revealing new things that weren't already revealed by the sentence that it's inferred from. But that's a really strange case. A or AB come by honestly does support B. And it's the same with the, it's the exact same with the infinitary case. So I'll just go to the very last couple lines. Learning E has, by default, a chance of presenting any T maker. That presumption is defeated if it piggybacks on learning D, which is not at all about the coin in question. Blah, blah, blah. Remote learning. What is it for OE to present something? Well, this has a stipulative aspect. Only epsilons are presented. Only T makers are presented, or DT makers. We've expanded the class of epsilons. Not all of them, though, presumably. It could be that, as we saw in some of our examples, there's no chance that you saw both Al's coin and Betty's coin coming up heads. So what sets the probability of epsilon being presented? This is, I have just a picture or a model to offer. So learning E is like glimpsing its makers, DT makers, through a glass darkly. The probability that that epsilon was presented is greater than 0 if one could say later, so that was you the whole time. Probability is high if one could add, as I suspected, low if who'd have thunk. So it's kind of like seeing someone in a picture. No, but the seeing aspect ought to make you suspicious. The model seems to depend on our seeing or sensing that E, but we might read it or be told that E. But language is actually brilliant at conveying source information. In fact, there are lots of languages where you can't say anything without adding a suffix that sort of conveys like huge amount of detail about what time of day you heard it and what the color shirt the person who told you was wearing and such like. I'm exaggerating. So truth makers provide an initial filter. So the way we know that the event of A learning wasn't showing you beta is that beta is not a truth maker for A. Which sentence is used can be instructive, even where the truth makers agree. The sentence can be instructive about which were on display. So let's just suppose that E, F, and G have the same truth makers. E is not the case that no coins came up heads. So that's definitely, that is not putting Al heads before you or beta heads before you or both of them before you. And probability of both heads is a third. Someone says a certain coin came up heads. Just grant me that that is the same truth makers, alpha, beta, and alpha, beta. Well, a certain coin came up heads. Intuitively, it's a chance that it was Al's, chance that it was Beta's, that it was Betty's. There's no chance that you were hearing about both, but it could have been both. And now the probability of both is a half. I haven't argued that, but you can argue it. A certain number of coins came up heads, where the number, a non-zero number, that's 1 or 2. Now, the logical thing to do would be to use indifference and say, well, The number could have been 1, it could have been 2. If it was 1, then there's a quarter of then there's a half a chance you were hearing about Al's coin, half a chance you were hearing about Betty's. So a quarter for each of, I'm hearing about Al's coin coming up heads, and I'm hearing about Betty's. It's also half a chance that you're hearing about both coming up heads, in which case the probability of the conjunction is 3/4. There's lots to be learned here from the semantics literature on evidential meaning and specificity. Someone says durian must be smelly. Maybe you see people kind of picking it up and sniffing it in a market, and you see their reaction. That signals you have indirect access to durian smell. Durian smells yuck, signals direct. It's the acquaintance inference. If you say something tastes good, you could have read that in a restaurant review. If you say it is so yummy, that suggests that you know firsthand. I want to say, and there's precedent for this, a certain F is G suggests that there's a thing that's F, and this very message is sourced in that thing's being G. And if you actually encountered that F later, you could say, so you are the rumored someone. So a certain coin landed heads presents itself as sent our way by a particular coin. The speaker may not know which or their informant either. Back through the centuries, maybe nobody who's been alive for many years knows. Still one landed heads, and that's enough to lift probability of both did from 1/3 to 1/2. But and this is a objection that Bob Stolniker made to me, although he also saw the answer. Can't this always be done? Let's introduce the term headsy. Headsy is the heads if there's only one. Otherwise, a head's picked at random. Probability of the other coin, call it other Z, landing heads is 1/2, right? Because it's not headsy. So the probability of A and B is 1/2, in this case, 2. That's the fallacy that Gardner was warning against. The probability that other Z landed heads is not 1/2 probability, given how other Z was chosen. It's either there was a forced choice, so headsy was picked as the one heads, in which case other Z is definitely tails. So it's 0 times probability of forced choice, plus 1 times the probability of an unforced choice. So that's 1/3. So you get the same answer as before, 1/3. Now, other Z may be righty. They may be the same coin. They, so to speak, differ probabilistically because of how they came by those names. I could really run this without names that might be in some ways better and easier. This raises all sorts of two-dimensionality issues. But I'm just going to finesse all that. To be righty is independent of how the coin landed. Its status as being the coin on the right. It didn't earn that title by landing a certain way. But otherness is achieved in most cases by landing tails. Sort of like some achieve tailness and some have tailness sort of thrust upon them. Otherness almost has tailness thrust upon it. So a certain F seems to be one we're acquainted with and have in mind. But this is strange because we may be clueless about which F it is. You know, someone knew a long time ago. You probably know the joke about, did you hear? The Iliad wasn't written by Homer. It was another guy of the same name. You think about why that doesn't make sense. It's related to what we're talking about. So we may be clueless about which F it is. And anyway, why would the fact that we have a thing in mind be probabilistically relevant? So maybe we've got things the wrong way around here. Rather than acquaintance driving the probabilities, N, so named, counts as an object of our acquaintance if its status as N is independent of the question under discussion, like whether the coin came up heads. Okay, just about done. Sorry. So evidence acquired by engaging with the state of things where its subject matter is concerned, I want to call organically conceived. That's the normal way you find things out, by saying, oh, it's about this. Let's check that part of the world. Bayes' rule seems better adapted to immaculately conceived evidence, E's that appear fully formed in your belief blocks. Immaculate conception is not an everyday thing, however. Jeffrey's rule is more organic, but he partitions on external world hypotheses, EI, and you can't always observe your way to a distribution over EI is opinionated enough to form a partition. So P of both came up heads isn't seen, but inferred from the probability that alpha or alpha beta were seen. But observation does plausibly enable assessments of what our eyes are probably telling us, or the learning event is probably tracking or providing a window on that part of the world. Update on those assessments then. That is what ACON does. So Bayes says, my kind of formal epistemology is still basically in business, provided we make the small adjustment, which seems called for probably anyway in some cases. And Brentano says in a book, I don't know if he says it in this book, but I like the title, The True and the Evident. Absolutely. Though, as Brentano has also written, what is at first small is often large in the end. Thank you for your patience. That's it. Thanks.